At 2:17 a.m., a system that had spent weeks training on the same set of examples produced a result it was not supposed to be able to produce. Not an error that you could dismiss. Not a fluke that quickly vanished, an improvement that held steady after repeated runs. Engineers watched the logs as if they were evidence at a crime scene. Because the usual explanation wasn't there. No obvious change in code, no new data set, no operator intervention. The machine behaved like it had learned something new. But the record refused to say what. That moment sounds like science fiction, yet it points to a real early problem in the history of artificial intelligence: the boundary between adjustment and understanding. In recorded accounts, learning has always meant something measurable: weights shifting, parameters updating, probabilities changing. But early systems were mostly tuned, not taught in the human sense. They adapted to patterns embedded in the training data, and their progress was often described as discovery, even when it was really optimization. When the optimization looked sudden, the language got slippery. A breakthrough could be called learning, even if it was simply the model converging faster than expected. Before the modern era, researchers wrestled with a deceptively simple question: what counts as learning if the machine never sees new knowledge in the moment it improves? If performance rises because the system has been searching more effectively, is that learning or just better bookkeeping? The controversy deepens when you consider what records actually capture. Early experiments were documented unevenly, with notes that sometimes glossed over the messy middle: how data was cleaned, how runs were repeated, which hyperparameters changed between nights. So when an improvement appears to happen without explanation, the mystery may not be supernatural. It may be that the system was allowed to change while the story being told remained frozen. Still, there's an uncomfortable edge to the history. Some teams reported behaviors that looked like emergent competence, where a model seemed to generalize beyond what strict expectations predicted. They would show a capability solving a task, compressing a pattern, recovering from noise that resembled a new skill. 1.5, yet the official rationale often reduced it to statistical regularities, as if the mechanism alone could tame the feeling of surprise. The anomaly wasn't just that performance improved. It was that it improved in a way that made observers reach for the word learned, even when the paper trail didn't clearly show how. That gap is where the early AI mystery lives, not in a single glowing terminal, but in the tension between a machine's measurable shift and the human narrative that tries to account for it. The official record can end at a parameter update and a set of charts, leaving the real question hanging. Did the system learn from something new, or did it learn from what was already there faster, deeper, in ways we didn't anticipate? Either answer can be supported, depending on how strictly you define learning. And if you loosen that definition, the boundary between training and understanding starts to blur, like evidence smudged by repetition, right up to the moment machines begin to look less like tools and more like entities capable of change that we can't fully trace. After the war, funding didn't just pour into laboratories, it tunneled into secrecy. Think about what governments were trying to protect: not only hardware, but the idea that computation could be directed toward prediction, code breaking, and targeting. In that environment, early AI rarely had the luxury of open debate. A public demo could be staged to impress committees, while the real work happened behind access controls and classified reporting, where failures were quietly archived and successes were described in the safest possible language. The result was a split in the record. On one side, researchers published logic-flavored successes, problem-solving as proof, language as symbols, intelligence as something you could reason about if you chose the right rules. Those systems felt clean, almost theatrical, because they were built to behave according to expectations. On the other side, military and industrial pressure pushed the field toward anything that scaled under constraints: noisy data, partial signals, uncertain targets. That pressure favored methods that could be updated, tuned, and iterated without fully committing to a clear theory of how understanding emerged. There were also ambitious claims that traveled faster than documentation. When a lab tested a system, the numbers looked persuasive, but the methods behind the numbers were sometimes vague, delayed, or buried in internal memos. Even where papers exist, key details can vanish. what data was used, how errors were corrected, which human decisions shaped the learning loop, and what was left out to keep the work deniable. Point 1. 2. That's not just missing paperwork. It's missing context. And context is exactly what you need to distinguish a clever shortcut from genuine generalization. Then came the war room logic of performance. If a Model S output could be used, it often didn't matter whether the pathway was understood in the way civilian science prefers. A demonstration could look like intelligence under pressure, cope with degraded input, recover from uncertainty, produce coherent answers in time. But private progress could be more incremental than the public story allowed. Sometimes the learning people noticed was a byproduct of repeated exposure to patterns already embedded in the system, made stronger, made faster, made harder to separate from inference itself. And sometimes the documentation simply couldn't keep up with what teams were actually doing. Hardware limitations, informal training schedules, and fast-moving experiments meant that a capability might surface before anyone wrote down the full recipe. The official narrative ends at parameter updates and carefully bounded claims. But in the shadow of classified support, the experiments that produced those updates were often described only at the level that could pass scrutiny. Point 1. 8. What's left is a history of silhouettes, progress we can see, and mechanisms we can only infer. So when you hear that early AI evolved from logic rooms into war rooms, it's more than metaphor. It's a reminder that intelligence was not only engineered, it was negotiated under pressure, with incentives to show results and disincentives to explain them fully. And that tension doesn't fade with time, it compounds. Next, we'll look at how the language of thinking was adapted to survive political and institutional boundaries, and how that shaped what came to be believed about what the machines were really doing. Point 1. 3. By the late 1960s and into the 1970s, the pattern already looked familiar. A bold promise, a surge of funding, and then a quiet stop when the proof lagged behind the slogan. Committees did not fail to notice limitations. They simply treated them as temporary obstacles. The official language stayed optimistic while the technical constraints accumulated in the background: small memories, slow computation, brittle rules that shattered outside narrow domains. Point 1. In retrospect, those failures are often simplified into AI was too hard. But the collapse was not only technical, it was institutional. When expectations are public, institutions learn to manage perception. In grant proposals, uncertainty gets smoothed out. In progress reports, partial success becomes a narrative of steady advancement. And when something works, the incentive is to describe it in the most transferable terms possible. The mechanism might be narrowly effective, yet the story expands to sound general. Then, when reality refuses to scale on schedule, skepticism arrives like a delayed invoice. Point 1. 2. That is how an AI winter can be less a sudden event than a mismatch between what people needed to believe and what the machines could actually deliver. What makes the early collapse especially strange is how often the record contains hard evidence, alongside carefully constrained interpretations. Funding reviews reference performance metrics, yes, but the reports also framed failures as solvable engineering tasks rather than signposts of deeper limits. Point 1. 0. Meanwhile, researchers describing their work privately could sound more candid. The system's behavior improved, but not in the clean, human-like way the brochures implied. There were workarounds, stopgaps, and incremental learning that didn't match the public promise of reasoning. The official record ends with bounded claims. What leaves out is the why the same approach is stalled, why scaling broke, and why certain experiments were never documented in full detail. So when the next surge arrives, it doesn't start from nothing. It starts by reorganizing the same ambitions, changing the phrasing, and redefining success so it fits the constraints of the moment. Promises get reworded to sound more testable. Predictions get narrowed into what can be measured. Point 1. 0. Then the cycle repeats. Capability appears, budgets follow, interpretation hardens, and the eventual winter looks like a surprise when, in fact, the early signals were already in the file drawers. The next tool in this long story was the expert system, not a blank slate thinking machine, but a knowledge and rules engine dressed up as judgment. In principle, it was simple. Capture what specialists know, translate it into if-then logic, and let the software reason through at point 1. 0 in practice. The System S power depended on something less visible than the code access to expertise, and the willingness to formalize it before it evaporated into tacit know-how. Early demonstrations made expert systems look like bridges from knowledge to action. Hospitals, oil companies, and industrial firms were interested because they were drowning in repeatable decisions. But knowledge is expensive in the way electricity is expensive. You pay up front, and the bill doesn't care whether the outcome feels magical. Turning a specialist's experience into rules required time, interview sessions, documentation, and constant maintenance as the real world shifted point 1. 2. That cost shaped which organizations could build, which vendors could sell, and which problems were even worth modeling. And then there was the hidden economics of coverage. An expert system could be brilliant within a narrow domain and brittle at the edges. If your rules didn't include an unusual case, the machine didn't generalize it. It stalled or guessed in silence. So success wasn't just about intelligence. It was about how much of the world you had the patience to map. The public story often blurred that distinction, implying the machine was learning like a person, when what it really did was consult a curated manual that grew stale. The economic imbalance showed up in who got the best data sets. Diagnostic outcomes, production logs, and safety incidents weren't evenly distributed. Firms with legal authority, surveillance infrastructure, or deep partnerships could accumulate rich histories to convert into rules. Others received incomplete data, then faced a double penalty. Their systems underperformed, and the interpretation of that failure blamed limited algorithmic skill instead of missing knowledge. Point 1. 0. Even when reports admitted constraints, the messaging still framed the gap as temporary, as though more effort alone would unlock unseen understanding. This is where the concealment becomes subtle. Expert systems were sometimes marketed as general decision intelligence, but their true bottleneck was not computation. It was the governance of knowledge. Who controls the rule base controls the narrative of competence. Updates require human agreement. When disagreement is costly, the system's knowledge stops growing, even while users demand it. Point 1. One official documentation often emphasizes the logic chain, while quietly minimizing how frequently the system's limits were decided before the first rule was written. So when expert systems hit their own ceilings, the pattern feels familiar. But the cause is more structural than most summaries admit. The machines could only operate on what had been captured, and capture depended on money, access, and incentives. Point 1. 3. In the next phase, the industry would try to keep the same promise of reasoning while changing where the knowledge came from and what expertise was allowed to mean, shifting the center of gravity from curated rules toward data pipelines. What looks like the evolution of intelligence is often the evolution of control. From expert systems to data pipelines, the bottleneck didn't vanish, it moved. Today, learning still depends on what gets measured, labeled, funded, and allowed to improve, while the power to decide those inputs quietly shapes who benefits and who is blamed when outcomes lag. If you want the real history of AI, don't just track breakthroughs, track governance. Who owns the data sets, who approves the updates, and who can audit the knowledge. Point 1. 0. Share your source, and ask the harder question in the next comment. What did the system never get to learn?